here. Okay. So let me begin with the talk. So the title, as I mentioned, is the non-uniform Hrushovski-Weil estimates. So all schemes in this talk are going to be separated over Z, and just to be clear, varieties are geometrically integral finite type schemes over K. Okay, so let me begin with sort of the way things happen historically. So in 1954, that is the pre-Deligne Weil 2 era, Lang and Weil obtained the following estimates. So let K be a finite field with Q elements, and let V inside P and K be a projective variety of dimension R and degree D. Then what they proved is that the number of K-valued points of V grows as Q to the power R, and the error term looks like D minus 1 times D minus 2 to the power Q to the power R minus half, and then other terms of order Q to the power R minus 1. Note that here Q is the number of elements in K, and so sort of there are two aspects to this. It first of all tells you that the number of K rational points grows as Q to the power R, and moreover, all the sort of coefficients in the error term are numbers which are uniform in N, D, and R. So that is, they only depend on the degree and dimension, right? And a modern point of view to sort of look at star would be to see this as a consequence of Deligne Weil 2, the trace formula, and constructibility. Right? So this is kind of follow from much more simpler techniques, rather a lot of machinery, but immediate consequence of those machinery than what Lang and Weil had at that time. In 1996, Hrushovski, while working on model theory of difference fields, obtained the following generalization of the Lang-Weil estimate. So this was something which he needed to complete his work on model theory of difference fields. So what I'm going to do is now state these estimates. So these are going to be the main object of this lecture. So let's see. So let K be an algebraically closed field of characteristic P greater than 0. So in particular, K K doesn't necessarily have to be an algebraic closure of a finite field. It could be something larger. And let's say X inside A and K be an affine variety. And we're going to denote by X twisted by Q inside A and K the corresponding Frobenius twist. So by that, what I mean is you have this nice Cartesian diagram, and you have this map X to XQ given by the Frobenius. And let C inside X cross XQ be an arbitrary subscheme. And I'm going to sort of use the word correspondence for the subscheme, and I'm going to denote by C1 and C2 the projections onto X and X twisted by Q. And we're also going to assume that C2 is quasi-finite. This is if you want to think of it, C is like the graph of a multi-valued function. So this is like the typical correspondence that you might be interested in. So the following is Hrushovski's theorem. For any integers n, d1, and d2 non-negative, there exists a constant mn, d1, and d2 such that for any choice of k, x, and c above, so that is any choice of the algebraically closed field K, this scheme X, and this correspondence C, with degree of X bar, you see X lives inside An, so X bar is going to live inside Pn, so degree of X bar less than or equal to D1, degree of C bar less than or equal to D2, and Q sufficiently large, meaning Q at least Mn, D1, and D2. What he shows is that the intersection of C with the graph of the Frobenius is finite, right? Note that C was this correspondence inside X cross XQ, and there is this God-given correspondence inside X cross XQ, which is the graph of the Frobenius. And what one is claiming is that for Q sufficiently large, depending only on the degrees, like only on these sort of basic parameters, this intersection is going to be finite. Moreover, if one assumes that the first projection, C1, is dominant, then in fact, one can give a very nice estimate to the number of points. The number of points actually grows as delta over delta prime times Q to the power dimension X. And the error term is like Q to the power dimension X minus half, where again, you have some constant which only depends on the degree and the dimension of the embedding. Note here that delta is the degree of C1, and delta prime is the inseparable degree of C2. So these sort of statements so this is really a statement in an algebraic geometry. This is a very basic statement which tells you about how arbitrary correspondences intersect with the graph of the Frobenius, and the point of view that we're going to take in this lecture is, as will be clear from the nature of the proof, that this is really a statement about topology of varieties and the topology of maps between varieties or correspondences between varieties. So that's the point of view that we are going to take. And in this talk, we are going to focus on a very specific version of these estimates, namely the non-uniform version. So before I go ahead and state these non-uniform version, I should mention that in this yet to be published note of Hrushovski, he uses techniques from model theory or intersection theory, and it's a really sort of eclectic mixture of things which leads to this estimate, right? So now in this talk, we're going to focus on the non-uniform version of these estimates, and I think they are significantly easier to state than the uniform version, and then we should probably spend some time understanding the setup in the non-uniform case. So in the rest of this talk, I'm going to assume that K is an algebraic closure of a finite field FQ, and that C from C to X cross X is a morphism of schemes with C2 quasi-finite, right? And I'm also going to assume that X is defined over FQ, and let's say X naught over FQ is the chosen model. And I'm going to denote by delta n the graph of the nth iterate of the Frobenius. Now note that since X is defined over FQ, the Frobenius with respect to Q is really a self-map, right? So I can keep iterating it. I'm going to get self-maps of X to itself. And in this very specific setup, it's easy to see that the inverse image of the nth iterate or the graph of the nth iterate of the Frobenius under C is in fact the fixed point of another correspondence, which we are going to denote by C twisted by n. And C twisted by n is simply this new correspondence which you obtained from C by leaving the second projection as it is, and you twist the first Frobenius the first projection by the nth iterate of the Frobenius, right? So you had this correspondence C. From this correspondence C, you produced a sequence of correspondences C twisted by n, and the object that you're really interested in, which is C inverse delta twisted by n, is actually the fixed point of some other correspondence. So in this very specific scenario, when you are over FQ, you have this sort of nice point of view to what you're interested in. So under these assumptions, one can prove the following things. So there exists a number capital N, so that for all n greater or equal to n, the fixed point scheme is actually finite over K, and that there exists a constant m, so that fixed Cn grows as m times q to the power n times dimension x. So this is finite, and then there is an upper bound to the growth, which is exponential mq to the power dimension x. And moreover, if you kind of take all these finite numbers together, put them in a formal power series, it turns out that this formal power series is in fact a rational function. And in addition, if one assumes that C and X are irreducible, so if one assumes that in fact C and X are varieties, and that C1 is dominant, then in fact one can give an estimate which looks exactly like what you'd expect from Hrushovski's theorem, that the number of fixed points grow as delta over delta prime to the power q to the power times q to the power n times dimension x, and the error term is q to the power n times dimension x minus half. Right. So this is and if you just stare at it, it's clear that 1 and 3 are immediate corollaries of Hrushovski's theorem, and in fact one is not claiming any any uniform any claims of uniformity about M. And I should also note that 2 is a consequence of the techniques which go into the proof of 1 and 3, answering a question of Hrushovski himself. Okay, now, yeah, okay. So before I proceed, are there any questions about the statement? Okay, so let me first state, a very nice corollary of the following theorem under the assumptions of three. That is, if you assume the correspondence C is such that it's dominant under the first projection and quasi-finite under the second projection, and everything in sight is irreducible, then in fact, this limit n tends to infinity, the number of elements or number of points in the fixed set divided by q to the power n times dimension x is actually delta over delta prime, which in particular is a non-negative number, is a non-zero number. Sorry, which means that this numerator, the number of points in the fixed point set, is necessarily non-zero for n sufficiently large, which means fixed Cn is non-empty for n sufficiently large. And this is a pure sort of algebrogeometric statement, which is again true for any correspondences satisfying these assumptions, right? And this corollary itself actually turned out to be very useful in arithmetic geometry, in group theory, in algebraic dynamics. So for example, it's used by Eno and Mehta in the proof of Gieseker's conjecture in group theory. It shows up in Borisov-Safir's work in algebraic dynamics. It's used in the work of Fakhruddin and Emmerich. So this corollary, sort of has turned out to be super useful in sort of various in various things. And so, for example, this corollary implies that if you have a dominant morphism of a scheme over FQ bar, then the set of closed periodic points of F are Zariski dense. So this is something which was observed by Fakhruddin and Poonen. And hence it became clear that one should really look for proof, or one should try to prove Hrushovski's estimates using standard techniques from algebraic geometry and arithmetic geometry, clearly because it turned out to be so useful. And there were some attempts at this point in order to prove this using very standard techniques. And the first successful attempt towards proving these estimates were due to Hrushovski. In fact, what he showed is using techniques from intersection theory, he proved not the full estimates, but he could show that fixed Cn is non-empty for n sufficiently large. So sort of this particular consequence of this corollary was something which Hrushovski could show without any using very standard techniques and without reference to Hrushovski's work himself. Right. So in this talk, what we're going to do is we are going to I'm going to try to indicate a proof and really more basically the ideas that go behind the proof of this result. Okay, now before I go ahead, here's just a quick sanity check, right? I mean, just to make sure that all the constants and all the form of these estimates are exactly what you think they should be. Now, suppose I took so the most basic example of such a correspondence C would be the graph of the Frobenius, and in which case you just want to get the usual sort of Langevin estimates back. The sort of slightly more non-trivial example would be when you take for C the graph of Frobenius itself, right? Then clearly, if you intersect the graph of Frobenius with the graph of the iterates of the Frobenius, this is only going to be finite when you take at least the second iterate, right? So it's clear that this claim about fixed Cn being finite for n sufficiently large is in fact necessary. You need a sufficiently large twist. Moreover, it's clear that if you intersect the nth iterate, the graph of the nth iterate of the Frobenius with the graph of the Frobenius, this intersection actually counts the number of fqn-1 valued points of x, which in fact one knows grows as q to the power n-1 times dimension x, which you can write as q to the power n times dimension x by q to the power dimension x. And note that this is simply the inseparable degree of the Frobenius, which is the C2 when you look at this correspondence. So in fact, this factor delta over delta prime is essential. I mean, there's no way of getting rid. It's kind of easy to see that you need to have a delta, but it's also important that you have a delta prime. Okay. Right. So Are there any questions at this point?
Yeah. So you said the first successful attempt to prove the corollary due to Hrushovski. Then do it implicitly means that Hrushovski's proof has some problem?
Sorry. Can you repeat the question? I'm really sorry, I couldn't hear you.
Yeah. So you say this one the first successful attempt towards to prove.
Yeah.
Then what's the problem of Hrushovski's proof? Original
Oh,
proof?
okay. So if I understand correctly, what you're asking is Warshawski proved the corollary. Why couldn't it be used to prove Hrushovski's theorem? Is that what you're saying?
I mean, so you said the first successful attempt to prove the corollary, but
right.
Hrushovski has proved it, right?
That is true. That is true. That absolutely is true. What I was trying to suggest is the first successful attempt using standard techniques from sort of algebraic geometry, which sort of is the kind of thing Warshawski had been interested in, and LA and NO and a lot of people. I mean, they've been interested in sort of giving a more standard proof.
Using model theory.
Correct, without using model theory and sort of within the domain of usual techniques from algebraic geometry. Absolutely, that's what I meant. Okay. And because all these results are kind of immediate consequence of what Hrushovski does. Absolutely. Okay. Right. Okay. So now I'm going to okay. So the rest of this talk, I'm going to focus on the proof of theorem A over here, and in the process, we'll see some possibly interesting results in certain other directions. Right. So step one is using very elementary induction arguments. One can in fact assume that X is smooth over K and that C2 is et al. And in fact, one can quite easily show that it suffices to prove theorem A under the assumptions of 3, which means one can assume C and X are irreducible and that C1 is dominant. So one is very quickly reduced to sort of these very basic assumptions, and more importantly, what one can show using again the techniques which Warshawski uses in his proof of this corollary, that there exists a compactification C bar of C, which is locally invariant along the boundary. Okay, so I'm not going to define this term locally invariant along the boundary. I just want to mention that what this means is you're going to take this compactification which you started with, you are going to compactify the entire correspondence, and locally invariant along the boundary is a condition on the topological behavior of C1 bar and C2 bar on X bar minus X. So it's some it's a set theoretic or a topological condition, but it is really useful, right? And we'll kind of discuss more about this later in this talk. Okay, step 2. Ultimately, what we want to do is we want to obtain these estimates via a trace formula argument, or to be more specific, and we want to use the Lefschetz-Verdier trace formula, right? So let's say, unlike the proofs of Hrushovski and Warshawski, this proof is l-adic in nature, and we really are going to be dealing with sort of possibly singular varieties here, and so we need this broader formalism of the Lefschetz-Verdier trace formula. Okay. Now let A from so I'm just going to very briefly recall the Lefschetz-Verdier trace formula, because there are some key definitions there which we need for the rest of this talk. Okay, so let a small a from capital A to y cross y be a diagram, and I'm going to think of capital A as a correspondence from y to itself. And let F be a sheaf on capital Y, right? So let U from Hom A1 upper star F to A2 upper shriek F be a cohomological correspondence lifting A, right? So U is a morphism in the derived category between these two sheaves, and this morphism is said to be a cohomological correspondence lifting the original sort of actual correspondence small a, right? Now, the reason why one is interested in U is just going to become clear in a moment. Now, associated to this choice of a correspondence and cohomological correspondence, one can define two numbers, two invariants called the global term and the local term. Like suppose A1 is proper, then note that you have morphisms from the compactly supported cohomology of Y with coefficients in F to, you can pull this back, go to A with coefficients in A1 upper star F. Then using the cohomological correspondence, you can change coefficients to A2 upper streak F. And finally, you can trace down using A2 lower streak and go all the way again to the compactly supported cohomology of Y with coefficients in F. So in short, what a cohomological correspondence does is it allows you to produce an endomorphism of the compactly supported cohomology of Y with coefficients in F. So that's in some sense the point of having this cohomological correspondence over here. And once you have this endomorphism, it's easy to produce a QL bar number simply by taking the alternating sum of the traces acting on cohomology. So this is the global term associated to any cohomological correspondence. Okay, now there is also again, just like any trace formula, which correspond. There's a global term and there's going to be a local term. The local term is slightly more intricate to define, but the general sort of mechanism here is that there exists a natural trace map from this space of cohomological correspondences to H0 of fix A with values in K fix A. So here K fix A is the dualizing sheaf on fix A. So you always have such a map. And if you further assume that fix A is proper, you can trace down all the way to QL bar. And this allows you to produce a number which, as the name suggests, keeps track of the local invariants. And it's simply this composite morphism. So LT of U is the image of U under this map. Note that U is a cohomological correspondence, so it lives here. Okay, so these are the sort of the two players in this game. And what the theorem of Verdier tells us is that if one assumes A and Y to be proper, then in fact the local term of U is in fact equal to the global term of U. Note that the global term was computed using certain actions on cohomology, while the local term, which I haven't quite defined, is local in nature and is defined using this diagram over here. Okay, so we want to use some such mechanism. However, the one thing that I want you to observe is that the theorem of Verdier only makes sense when you have a proper correspondence, right? And in this in some sense has been the basic problem that one has to deal with, be it in Hrushovski's proof or Warshawski's proof of the corollary or this proof. The correspondence that you're trying to work with is not necessarily proper, and this leads to various problems. And so the most obvious thing to do is kind of compactify it, which is okay. But then, of course, you get some boundary and you possibly add some singularities, and sort of what all these what Hrushovski, what Warshawski, or what I do is kind of find a work around this problem, right? Okay, so now our aim, so let's go to step 3. Step 3 is about, so note that in order to play this game of Lefschetz-Verdier, you need a correspondence like this, a correspondence where all these schemes are proper. You need a sheaf, and you need a cohomological correspondence of the sheaf. So this is the input for a Lefschetz-Verdier trace formula, right? So our aim will be to apply the Lefschetz-Verdier trace formula to a suitable Weil sheaf F on X bar and a cohomological correspondence U of F lifting this compactified correspondence C bar, right? And the reason we want a Weil sheaf on X bar is because we just don't want to lift U. We actually want to lift U, so that as you remember in the sort of the main statement of the theorem, there is this correspondence C, but there are also these sequence of correspondences C twisted by N, right? So what we want to do is not only produce a cohomological correspondence lifting C, but we want to produce a sequence of cohomological correspondences lifting each of these twists, right? So that's the and that's what we want to do. And in order to do it, do such a thing, it would be good if we began with a Weil sheaf on X bar, right? And note that unlike C2 bar may not be étal or X bar be smooth, right? However, since C bar has a locally invariant boundary, one can ensure that for n sufficiently large, the local terms of this un actually decompose as local terms of un restricted to the open part, right? So there is this thing which I'm interested in. It breaks down into the local term of something which is only dependent on this open set X, and local term of something which is restricted to the boundary, right? So I want to compute the local terms. I have compactified, so I have gained some boundary, and luckily I can ensure such a decomposition. And this decomposition, in fact, follows from the work of Hrushovski, Fujiwara, and Pink, their work around Delisle's conjecture. So the fact that you can always guarantee such a decomposition for n sufficiently large, and this is exactly where this local invariance of boundary becomes important, right? Okay, so now one is actually set. One can actually hope to do something with this mechanism, and our hope now is to find a good enough sheaf F and a good enough cohomological correspondence U such that the global terms grow as delta over delta prime to the power times q to the power n times dimension x with an error term of what we want. We want this local term on the open set to count exactly what we want, that is the number of fixed points of Cn. And we want the local terms on the boundary, again, to grow not too fast. This should grow, not faster than the error. So if we can find such a sheaf F and we can find such a cohomological correspondence, then using the Lefschetz-Wathier trace formula and this decomposition, we would hopefully have a proof of these estimates. Okay, so this is a good midpoint. So are there any questions? Okay, yeah. So of all these three things that we demand, the easiest to actually ensure is B. In fact, one can choose F in such a way that its restriction to X is actually QL bar, and one can choose U in a way such that its restriction to X is the morphism, C1 upper star QL bar, which is just QL bar, and you choose this isomorphism with C2 upper shriek. Note that X is étal and C2 is étal. So, X is smooth and C2 is étal. So there exists such an isomorphism, right? So generically speaking, we know what F has to be and what this cohomological correspondence U has to be, right? So generically, we have some sort of normalization for these choices, right? However, we have the following issues immediately. So problem one is there is no natural map from C1 bar upper star QL bar to C2 bar upper shriek QL bar. Note that C2 bar is no more étal. So in fact, you cannot just take the sheaf QL bar and hope to produce a cohomological correspondence on the entire scheme X bar, right? So there are two problems now. In fact, you do not know, it's not clear how to extend the sheaf F from which is QL bar on this open set. Moreover, if we also didn't manage to extend the sheaf, we should also find a way of extending this cohomological correspondence, right? So that's problem one. And problem two, and this is the more serious problem, namely, no matter how you choose to extend F and U, this other local term, which you want to estimate, which is the local term along the boundary, is usually not the local term of a proper correspondence. In fact, more often than not, it's the local term of a non-proper correspondence. So things would have been really nice if, for example, you could apply Lefschetz-Wathier here, Lefschetz-Wathier here, and then you'd be done. But unfortunately, the second term is something which cannot be estimated using the Lefschetz-Wathier. So because it's something non-proper, and local terms are usually very hard to compute explicitly. So on very nice situations, you can do that, but typically they are very hard to kind of estimate. And one is in fact trying to do that in a non-proper situation, right? So so what do we do? So here's the sort of the more kind of so for problem one, in fact, what one ends up doing for many reasons, and I'm going to mention a few reasons here. In fact, the right choice of F is the intersection complex of X bar. So this is not quite the constant sheaf. This is what I mean. For example, the constant sheaf, appropriately shifted if X bar were smooth. But more generally, this is a sort of an extension of the constant sheaf from the smooth locus, and this sheaf has many nice properties. So, for example, restricted to X, it's in fact the constant sheaf shifted by dimension X, and more importantly, when you restrict it to the boundary, so of course you have some control of what happens on the open part, but when you restrict it to the boundary, it in fact lies in what's called perversity less than or equal to -1. Now, this is a condition on the dimension of supports of the cohomology sheaves of this complex, and as we'll see later, this condition is really crucial, right? And one has some estimates on the cohomological dimension of ICX bar. It has only non-zero cohomologies between minus dimension X to dimension X. It's also pure of weight dimension X, again, something which we will crucially use to bound the global term. And moreover, one can actually produce a non-canonical extension U of non-canonical extension of this cohomological correspondence which one had on the open part. So there exists this U from C1 bar upper star ICX bar to C2 bar upper shriek ICX bar, whose restriction to X is exactly what you want. Right. So I should point out that such cohomological correspondences are constructed using geometric semi-simplicity of pure power sheaves and the composition of a pure complex into its shifted perverse cohomologies. Right. So there is unless this cohomological correspondence, unless this correspondence C is something geometric in nature, there is no such canonical choice. Right. So, for example, C could have been the graph of the Frobenius, in which case we would know exactly what to do here. Right. But more generally, when C doesn't arise from some, some very natural process, one has to kind of make a choice of such correspondence. But the nice thing is one can always guarantee generically what happens. And somehow this is the crucial point, that generically all of these extensions behave the same way. Right. Now, once you have this, once you start with the intersection complex and this cohomological correspondence of the intersection complex, in fact, the issues A and B are both resolved. Namely, one already has a good control over the global terms, because you know that the intersection complex is pure of weight dimension X. One can also ensure that the local terms on the open part are computing exactly what you want, because there is a normalization to this cohomological correspondence. So the only thing that we are left to deal with is how to bound the local terms of this cohomological correspondence restricted to the boundary, which, as I observed, is not necessarily a proper correspondence anymore. Okay, so this is what's going to this is going to be the focus of the rest of this talk. Okay, in order to bound the local terms on the boundary, I have to introduce this new class of correspondence called as essentially proper correspondence. Right. So, again, are there any questions at this point before I move to the next section? Okay. Okay. So let me define what essentially proper correspondences are. So a correspondence, small b from B to Z cross Z is said to be essentially proper over FQ if Z is proper, right? So and there exists a commutative diagram such that so you have B to U, U to U being an open set inside Z cross Z. So such that you start with an arbitrary correspondence, you assume that Z is proper, and now you want to factor this correspondence like this, such that B bar U over here is proper, and this open set U is a very specific kind of open set. It's of the form union I, UI cross UI, where UI is a cover of Z defined over F, right? So such correspondences, one defines them to be essentially proper. Note that if B was already proper over K, then any proper correspondence is automatically proper because you could simply choose the cover to be Z itself. But that, of course, exists non-proper correspondences, which are essentially proper, and those would be the things of interest in this lecture. Now, why do we care about essentially proper correspondences? So first of all, note that since U is of the form union I UI cross UI, where UI is a cover of Z defined over FQ, even though U is an open set inside Z cross Z, it in fact has all these algebraic cycles, namely the graphs of the Frobenius inside, right? So that's the nice part. And since B bar U is proper, fix Bn turns out to be proper over K simply because this morphism is proper, right? So there's this nice property that it's an open set which contains all the graphs of the Frobenius or all iterates of the Frobenius, and there is a factorization like this. That's one thing. And more importantly, again, for the kind of things one ends up proving, it's obvious that U is, there is a Frobenius action on Z cross Z which preserves U, right? Of course, because U also is defined over FQ. But moreover, note that because of the very specific shape of U, U is in fact also stable under what one would call the partial Frobenius. Namely, one could take the Frobenius on the first factor here and the identity on the second factor. Now, if you choose an arbitrary open set of Z cross Z, there's no reason the partial Frobenius has to stabilize such an open set, but by sort of this almost product structure of U, in fact, the open set U has additional symmetries coming from the partial Frobenius on either sides, right? So these are the kind of sort of symmetries that we hope to capitalize on. Okay, now yeah. So as I noted, since the graphs of the Frobenius are inside U, the fixed point set of B twisted by N is all proper over K, and hence, given any cohomological correspondence U, one can make sense of the local terms. Note that the only sort of obstruction to producing a local term is the fixed point set being proper. And the moment the fixed point set is proper, one can produce these numbers, even though the global term may not be defined, right? So for the global term to be defined, the first projection has to be proper, which need not be the case, but for an essentially proper correspondence, these local terms, these numbers are always defined. Okay, so now I'm sort of ready to state theorem B. So there's a theorem A, this is the theorem B. So let X naught over FQ be proper, and let F naught on X naught be a mixed sheaf of weight at most W and perversity at most A, right? Then for any essentially proper correspondence, C naught to X naught cross X naught, a cohomological correspondence U lifting C naught, and any epsilon greater than 0. So you have a scheme X naught, you have a mixed sheaf of bounded weight and perversity on it, and an essentially proper correspondence, and a cohomological correspondence lifting this essentially proper correspondence, right? So you start with this data, which has been the setup so far in this lecture, and fix any epsilon greater than 0 a positive number. Then the claim is there exists an n epsilon such that for all n greater or equal to n epsilon, that is for all n sufficiently large, in fact, there is a bound on the local terms of un, which grows as q to the power n times weight plus perversity plus dimension by 2 plus epsilon, right? So again, the point is, even though this local term does not necessarily correspond to a global term, because this essentially proper correspondence may not be proper, however, it's still possible to bound this. And just to be precise, when I say norm, these are all l-adic numbers. I'm going to fix an embedding of QL inside C, and then I'm going to look at this norm, and M in particular will depend on this embedding. So the point is, even though these may not correspond to any global terms, it is possible to bound them using what one would consider as global parameters, that is the weight, perversity, and the dimension, right? And of course, this is again just a theorem of independent interest about local terms of not necessarily proper correspondences. And we claim, in fact, that theorem B implies theorem A. Indeed, the correspondence C bar is an essentially proper correspondence over Z, right? So you had C bar, which was a correspondence from X bar to X bar. Z was the boundary. As it turns out, the boundary being locally invariant implies that if you restrict this correspondence to the boundary, it's in fact essentially proper. Moreover, note that the intersection complex restricted to the boundary has weight at most dimension X, and the perversity now, ICX bar is perverse. But when you restrict it to the boundary, you're going to get a perversity drop. So the perversity is going to be at most -1, and this perversity drop is the key. For example, if instead of ICX bar, had one chosen, possibly some other extension, one would not have been able to guarantee this in general. And thus, choosing epsilon equals half, in this result, if we choose epsilon to be half, what we get is that the local terms are bounded above by m times q to the power n times dimension x. This is the weight. We have -1 because of the perversity. And here we have dimension of z, which is at most dimension of x -1. So, we have a gain of a -1 plus -1 by 2, which means a -1. And then we have a loss of half. So overall, we gain a -half, right? So note that if we didn't have this perversity drop, or that is, we simply looked at sort of the estimates coming from the dimension drop, then we would have a factor of m times q to the power n times dimension x, which is the same as the leading term, and that would have been useless, right? So again, sort of, I just want to stress on the point that sort of the specific sheaf we chose was good for also the the computations of the global term and stuff, but it is also important that one works with ICX bar because one needs this perversity drop when one restricts to the boundary. Okay, so are there any questions here at this point?
What is n in your theorem B?
N over here? Is this the n you're talking about?
M, the capital N.
Oh, m is some constant. M is some constant. So m is some constant which depends on the embedding of Qn inside C.
So this m is the same as your theorem A.
Let's say the m of the theorem A is sort of max of a lot of other m's which occur in the picture, and one of the m's is this. Right. Okay. So finally, I also want to mention that, in fact, one proves something slightly stronger than this, and in fact, this is why one gets a rationality. One in fact shows that there is a vector space V over QL bar and a functional phi from V to QL bar, and an endomorphism T from V to itself, and an element small v of capital V, such that the local terms of u twisted by n are in fact obtained by evaluating this functional on the nth iterate of t acting on V. And this, in fact, gives the rationality. So note that usually, typically, the rationality statements that one sees in algebraic geometry is because you have some sort of trace acting on a vector space. In this case, we don't really have the trace of some endomorphism on a vector space, but we have this sort of functional, which in fact gives rise to this rationality. And more recently, there are others who have obtained sort of these rationality statements in slightly more general situations, right? Now I should sort of I should also mention that so there are some very obvious questions, right? So first of all, what is the obstruction to just sort of proving or getting the uniform estimates using these techniques, right? So at this point, I want to mention that very recently, me and Yakov Warshawski, we have a proof of the uniform estimates, meaning the actual sort of estimates of Hrushovski, and what we in fact do is use techniques from intersection theory and ideas similar to what Hrushovski had in his proof of the corollary to sort of prove these full estimates. So one in fact uses things like alteration. So one actually reduces to the case of a smooth projective variety to get these full estimates, right? So of course, our initial plan or motivation was to obtain a proof along the lines of these non-uniform estimates. Of course, there are a couple of reasons. One is the proof is very intrinsic. You don't make any choices. But more importantly, it also, one is also motivated to think about a question by Eno and Srinivas, namely that if one wants to think about, if one ends up thinking about the Weil estimates as some sort of analogs of the mixed thought structures on the cohomology of varieties over C, then what would be the sort of the analog in characteristic zero of the Hrushovski estimate? So as I said right in the beginning of the talk, so these estimates, whatever the nature may be, but fundamentally they're going to tell you something about the topology of varieties and topology of maps between varieties, and as is clear from the nature of the proof, it is really it's using some very basic properties of the intersection complex. And in fact, the trace formula suitably applied is, the shadow of this appears in this as the Hrushovski estimates. So the much of the techniques carry over to characteristic zero also, but one quite doesn't know what is the statement one has to guess as an analogous statement in characteristic zero, right? So that was sort of the some motivation, but then there are a couple of obstructions here to carrying over the proof to the uniform case. So first obstruction, sort of if one tried to kind of do it very naively, is one wouldn't actually know, one doesn't quite know, or rather it's conjecture, that the action of Frobenius on the cohomology with coefficients in, let's say, sheaves of geometric origin is semi-simple. This thing is conjecture. Had one known that, actually things would have been pretty simple at certain points to carry it over to the uniform case. One doesn't quite know that. But more importantly, what one would actually, what one does is, for example, we do this in the proof of the uniform estimates. We end up defining a norm on the Chow group of quasi-projective varieties, right? Now, this is quite essential in order to sort of carry out the proof, and a similar thing would be necessary if one were to carry out the proof using l-adic techniques. But now one would have to define a norm on the space of cohomological correspondences. But unlike the Chow group, which is or tensor with Q, which is a Q vector space, the space of cohomological correspondences is an l-adic vector space, and it's not quite clear how do you define a norm on such vector spaces, which is which has to of course satisfy some conditions, which I'm not going to go into, but that was like one obstruction. But I should also mention that very recently there is a work of Sabin, Kowalski, and Fourie, where they end up constructing what they call quantitative sheaf theory, where they end up constructing and Fresson, sorry, I forgot Fresson, where they end up constructing norms on l-adic sheaves on quasi-projective varieties, right? So if you think about it, if one were to actually construct norms on cohomological correspondences, a good starting point would be their work. So ideally, for the identity cohomological correspondence, whatever norm you construct should be the same as what they do, because it has very nice properties, and you would want to preserve all those properties. So that would be a good starting point, right? Okay, so thank you for your patience, and yeah, I'm done.